So hello, good afternoon. Thank you for attending my talk. I am Alberto Solera, a fourth-year PhD student in this program, under the supervision of Stefano Di Sietti and Carlos San Miguel, working at INTA. I will talk today about reduced order models for active flow control. Well, we know that we have a problem with climate change. It is worsening our floodings, heating or changing our climate. And there are some works that show that turbulence-related inefficiencies can account for about 10% of global greenhouse gas emissions. And in particular, drag in transport could represent about 5% of Europe greenhouse gas emissions. So if we want to keep transporting stuff, we need to be more efficient. And traditionally, this has been done with geometrical optimization, but there are obvious drawbacks in this approach. So we are moving to active flow control that uses actuators to inject flow or at least momentum into the general flow, and so we can modify the general structures according to our desires. However, there are still open problems to widespread implementation of active flow control in real vehicles. In particular, we will focus on reduced order models for control. The first question is whether a nonlinear model can capture the complex dynamics of high Reynolds number wakes and so on. We have a first paper on that. Then we test whether these more complex algorithms are able to not only compress more compact information, but also to predict compared to traditional linear models. And the third question is, can we actually build a controller to control a wake with practical constraints? And this is the third paper I will talk about. This is the first paper. It was published in Nature Communication a couple of years ago, so I have presented it like 3 or 4 times here. And here we show that this architecture, the beta variation autoencoder, it's a nonlinear model with a constraint regularization that promotes orthogonality in the latent space, so that we can compress the information in a much more compact latent space than the linear POD, from 70 modes to 10 or 20 modes, but still retaining some properties of the proper orthogonal decomposition. And here we also use the transformer that is able to use information for separated events in time. This is a wake flow with a large delay in the propagation of information. So moving to the next paper, here we test the different encoders and predictor architectures, but they share the same framework. We compress the data, we predict the latent space taking into account the control vector, and then we decode the field and see how well are we predicting the flow. We are using this 2 flow configuration, simplified 2D track or rectangle, and the fluidic pinball. And what we see is that actually the linear method, the proper orthogonal decomposition, is able to predict, to hold a good prediction for longer. And why? We can see the phase portrait here on the right, that the linear method produces a much simpler latent space coordinates that are easier to predict for the LSTM model. In particular, for the fluidic pinball, the most important coordinates don't produce even a recognizable cycle, but this is the field space with no apparent structure. So it's very difficult for even a nonlinear model predictor to represent that dynamics. For the final paper, we tackle the control problem. We first, in the simplified track, we first generate the dataset, and that is not easy because we would like to establish the wake, and this is an unstable position in the dynamics of the model. So we have to craft a control signal in open loop that somehow explores that unstable dynamics points. Using this dataset, we build the model and select as few sensors as possible. Using the model, we implement a model predictive control algorithm, and then we test this controller for noise, lag, and other practical issues. This is the structure of the model. We use a series of past sensor readings through an LSTM encoder that produces a latent space that then is mapped using neural networks to the aerodynamical forces, and also we use a predictor that accounts for the control, of course, to propagate the latent space into the future. The three models are trained simultaneously with some regularization terms, so that the latent space is well conditioned for the mapping to the aerodynamical forces and also to be predictable. As we have seen before, we need some structure in the latent space for it to be useful. We also use here the selection algorithm that ranks the sensors according to their marginal contribution to the results of the neural network, of the encoder. So we can rank them, and we see that only using 4 sensors in the back of the body, we can effectively control the flow. With those 4 sensors, we achieve a 13% reduction, we reduce the lateral forces, and we see that the model is also quite robust to delay in sensing. We can use information from half the horizon time in the past and still achieve a drag reduction. And we also have a quite robust model to noise in sensing. What is more important, the model shows a gradual degradation where we abandon the training distribution dynamics. So the prediction degrade, but not catastrophically fail. We can see that we do not achieve the wake stabilization, but still we can reduce the drag. In the graph animation, we see the yellower points are farther into the model predictive horizon, and as they turn green, they approach the final black values. So the planning is to finish the ongoing 2 paper reviews and hopefully defend the thesis this year, in the following months. These are the achievements so far. We have the first paper in Nature Communications, and the second and third paper and the review at the Journal of Fluid Mechanics and Engineering Application of Artificial Intelligence. There was a first conference in Turin presented by Carlos with the results for the control algorithm. It was also presented by me in Malaga. In Dublin, I presented the second paper, the trade-off between linear and nonlinear methods. And next week, Carlos will present another new work in Paris. I wanted to highlight that the beta-brace autoencoder has been awarded as a highly cited paper in the Web of Science, placing in the top 1% of publications in engineering in the beginning of this year. So it has been quite successful. And that's all. Thank you for your attention, and I open to any question.